Hey there students, welcome to Psych 53 Lab, Module 9, where we'll be discussing multi-level modeling. So, just a little introduction to multi-level modeling. A multi-level model, which is also called random effects models, mixed effects models, and hierarchical linear models, there might be even more names that I'm not sure of, but is used to model hierarchical data. In data that arise from a hierarchical design, the upper levels are usually organizations or something like that, are selected from the population. Then cases, the employees of some sort are selected within these upper level units. In this way, employees are nested within organizations. So it's pretty similar to when we were running nested ANOVAs. Now we're running things in a regression framework. So what I'm going to go ahead and do, we're going to dig right into R, and I'm going to have lessons built in throughout this entire lesson. So here we go. Let's go ahead and open up R Studio. Okay, I'm going to go ahead and zoom in for y'all. There we go. Go ahead and create a new project, so new directory, new project. Name this, make sure it's saved in the correct directory. Yep. Name this module 09. Create that project. Perfect. Let's go ahead and download the data set. So we're going to scroll down to module 9. Module 9 lab, and it's going to be the mlmteams.csv. File, save as, browse. Browse it to that correct directory. Oops, desktop. Psych 63. Module 9. I'm just going to delete this one here to make it a little bit easier for us. Save. There we go. So we got the MLM teams loaded up, and let's go ahead and create a new R notebook. Go ahead and bring this down. Okay, delete this unnecessary text. Go ahead and name this multi-level modeling. Create our table of contents. POC, yes. Let's go ahead and save this. Name this module 9 notebook. Save. All right, there we go. Go ahead and got our Studio and notebook loaded up for us, ready to go. Got the mlmteams.csv loaded in. So next thing we're going to do, we're going to install some packages. And first thing I'm going to do is I'm going to load up some notes here real quick. We've got a lot of packages that we're going to load up. We're going to be installing 2 packages today. We're going to be installing the Mumin package, which is going to be used to calculate our pseudo R squared values, which will be explained later, and install the model R package, which is going to be used to help us build pretty good optional plots that I want to kind of show you, because I think it gets the idea across of what's going on with multi-level modeling. And then we have a lot of different packages. I don't think we're going to be running into any package conflicts here, so we should be good. So let's go ahead and do that. So we'll do hashtag load libraries to insert new R chunk. Okay, so we'll do install packages quote M, capital M, lowercase u, capital M, capital I, N. That's a complicated one, I know. Install packages quote model R in all lowercase. All right, then we're going to do library, tidyverse, library, LME4. Remember, that's for our random coefficient models, or our multi-level models, which we'll be using for it today. Our capital T test, that just makes it so we get significant values associated with our multi-level models. Library psych, library Mumin, and library model R. All right, this is going to take a little while to load up, so we've got installing 2 new packages and loading up about 5 different packages, or 6 actually. So here we go. Let it install those packages. So I'm installing the Mumin package. There we go. Installing the Model R package. There we go, and then loading in all our libraries. All right, should be good. I'm going to go ahead and hashtag out these two package installs. I'm just going to run this again just to get it all so we're clear. Okay, I'm going to save my notebook real quick. Let's go ahead and see what we got next. Okay, so I just want to give a description of the data set. So essentially, what we're doing here is a research team sought to determine an 8-week summer program designed to encourage female high school students to pursue data science education and career paths was more effective if the program was either team focused or individual focused. So they recruited 500 females who were recruited to participate in the program, which included a lot of different skills and assessments. Using these data, the researchers created an index that listed females into quantiles of their likelihood of success in the summer program. So the index ranged from 0 to 4, where 0 indicates the highest likelihood of success and 4 designates the lowest likelihood of success. So it's an indication of risk. Once this risk index was created, one female from each quintile was randomly assigned to teams of 5 students that each had one female who had a risk index of 0, one had a risk of 1, one had a risk of 2, and so forth. So this created a total of 100 teams, each with 5 team members. Next, each team was randomly assigned to participate in either a team-focused version of the program or an individual-focused version of the program. Following the random assignment, the teams participated in the 8-week program. Throughout the program, a series of measures and assessments were collected, and the data are all in this MLM teams.csv. And below is a summary of these variables. So we have team ID, which is just the team that they're on. Kid ID, which every student got a personal ID, and so keep in mind there's a team ID and there's a kid ID, the condition they're in, their risk quintile score, and their score on the knowledge comprehensive exam to measure knowledge that was gained at the end of the summer program. So it can range from 0 to 100. That's going to be our main outcome variable of interest. And then FRD. At the end of week 4, all students completed a measure of belief in communal affordance of a data science career to reach goals. So it ranged from 1 to 9, where higher scores denoted a stronger belief that career in data science allow for communal goals to be met. So that's the data set that we're going to be working with today. So let's go ahead and read in that data set. We're going to call it teams. So let's go ahead and do that. So let me go ahead and get to my R. So hashtag read in data, use insert, R chunk. So we're going to name this teams, use an assignment operator, use read underscore CSV, and then in quotation marks, MLM underscore teams dot CSV. We go ahead and read that in. So let's go and look at our data set. So as you can see, each kid has a distinct ID, and then the team ID that they're in, and then their score on the test. This is their comorbidity, and then their risk quantile score. So notice that each team has 0, 1, 2, 3, or 4 for each team, and then we have 0, 1, 2, 3, 4 for team 2, and so forth and so forth. So we've gone ahead and we've downloaded that in correctly. We have 500 observations. I'm not going to make you do any transformations to your data today. So just a little bit of the structure of the data. So level 1 variables, which is the individual level, is each student's ID number, risk index, and belief in communal affordances of STEM careers and final exam scores, which is the final exam score is going to be our outcome variable of interest. Level 2 is going to be each student's team number. So that's what they're grouped into. So when you're thinking level 2, think of what they're grouped into and the treatment condition as well that they're assigned to. So if they're grouped into something, it's more likely to be a level 2 variable. Okay, so before we run anything, I want to just go ahead and factor our variable. This isn't actually necessary, but it's going to be really necessary for some of the visualizations that we're going to be doing. So I want to go ahead and do that. But actually, before we do that, let's go ahead and just describe the data set. Describe data set. So let's do that. Describe and teams. Go and do that real quick. It's always so simple just to describe the data set. I don't know why I keep forgetting to put it into your slides, but here we go. So we have an average score of 73.22 and risk quintile score of 2 and so forth and so forth. So main outcome variable of interest is going to be our score. That's going to be our outcome variable for all this. It ranges from 0 to 100, but it looks like the low score is 21 and the highest score was 100% on the score on the test. Now let's go ahead and factor our variable. So let's go ahead and factor the team ID. Like I said, this isn't totally necessary to do for our analysis per se, but it's really nice to do for the visualizations that we're going to be doing. So it'll make things a lot easier for us later. So let's go ahead and do hashtag factor the team ID. Create a new R chunk there. I'm going to go and bring this up a little bit. Okay, just look at my notes real quick. Okay, so we're going to rewrite over the team's data set. We're going to use the mutate function. We're going to use the team's data set. And we're going to name a new variable called team_id.f to indicate that it's the factor version of team ID. Do factor team ID. So all that's doing is we're mutating the teamID.f, the teamID variable into a new variable called teamID.f. So we'll have 7 variables when we run this. So going to run that. We have 7 variables, and all teamID.f is the factored version of our teamID. And like I said, that's just going to make it easier for our visualizations a little bit later. So we've done that. Now let's go ahead and get something called the mean of means. We're going to go ahead and get this through a series of grouping and summarizing, in which case we are going to get the mean of means of this variable, and we're going to save it into an object so that we can call it back later. Okay, so to do that, we're going to do hashtag get mean of means. So essentially that means we're getting the mean of the mean variable. So what we're going to do, we're going to do team_means is this, and we're going to group by teams, comma, team ID, .f actually, and then we're going to do team means. We're going to use summarize team means, comma, mean_score equals mean score, comma, na.rm equals true. Then we're going to create a new object called mean of means, in which case we're going to use the summarize again on our team means variable, team means object, I should say. And then we're going to create a new variable called mean of means, equals mean score, comma, na.rm equals true. So we go ahead and run that, and I'm going to go ahead and just do one more thing where we're just going to spit out the mean of means. So should be good, assuming we don't have any errors. I think we're good. There we go. Looks like it ran. So our mean of means is 73.216. And we're going to be using this mean of means object that we created. So we have a new object called mean of means. We're going to be using that for some of our visuals in the later slides. Okay, so go ahead and type that in. Go ahead and do this. Just even it out. There we go. Go ahead and save. So we've gone ahead and created the mean of means. We're going to be pulling this number later. So we have an object in our environment called mean of means. So let's see what we got next. Okay, so whenever I'm creating visuals in this, rather than having you watch me type in everything, I'm going to simply just give you the code. You can copy and paste this code from the slideshow into your RStudio notebook. I'm just going to be copying and pasting it, but I'll explain to you what's going on. So essentially, we're creating a ggplot using the team's data set. We're using our x variable is teamid.f, our y variable is score. We create a geom box plot. We use the team summary to get the mean. The stat summary to get the mean of each team individually is what this is doing. We use the geom h line to draw the y-intercept, which is going to be the mean of means, and we're just going to set it so that there's a bar that shows what the average is of each team, the average overall of the whole team. The scale y continuous is going to set limits equals to set the y-axis 20 to 100 with breaks with going from 20 to 100 and breaking it by 10. Then we have some labels that we're setting in. We're setting a title, a subtitle, a title for our x-axis, and a title for our y-axis. And then the theme is just simply just the theme that we are, it's just a theme that I created just to make the graph look a little bit nicer. So I'm going to go ahead, I'm going to copy some code into it. You should be able to copy this from the slideshow, so you won't have to spend all this time, but let's do hashtag create visuals, create a new art chunk, and I'm just going to copy and paste some things in. So this should run appropriately, and it takes a little while to run. And there we go. What we've created from this is this series of box plots. So each team has its own individual box plot, so we can see the variability of each team there. This dashed line that we created here is the mean of means. So that's at that, what is it, 73.216. So this is the mean of means. So what I wanted to represent with this plot is show how much variability there is within team and between teams as well. And I wanted to try and represent that, because that's kind of what we're going to be modeling, is that you can't look at each of these teams individually. You can't group all these teams together because there's so much variation into the way that they do. So this is why teams is considered a second level variable within our data set here, because there's so much variation between teams, and we're going to be seeing how much of that variation is accounted for by teams essentially. So what we're going to be doing is we're going to be using the Elmer function again. So the Elmer function, as you recall from before, was when we were doing random coefficient modeling. Now we're going to be using it for the multi-level modeling. So we're going to be getting these groups and seeing how much variation is due in part to teams. So the way that we're going to do that is I'm going to simply be plugging it in, then I'm going to be telling you what the output shows. So additionally, we've learned about this in the last unit, but I want to just define fixed and random effects. Remember, fixed effects are those that do not vary over subjects or groups, the average value of the slope or the intercept. Additionally, we have random effects in which they might vary across subjects or groups. Intercepts and slopes might be calculated for each group or each subject to see if they vary meaningfully. And I think I'm going to have some visualizations that are going to make this a lot easier to see a little bit later. So another thing that we're going to be focusing on today is the interclass correlation, otherwise known as the ICC. This is the proportion of variance in a level 1 variable that is accounted for by a level 2 variable. So another way of interpreting this ICC, the way that I like to do, is the average correlation of a level 1 variable between two individuals in the same level 2 group. So in general, this is kind of like an effect size. An ICC greater than 0.2 generally indicates a meaningful level 2 effect. An ICC of greater than 0.05 is worth further investigation. So 0.2 is a meaningful effect, 0.05 is worth further investigation. And essentially the ICC, we're going to be doing it by hand, is calculated by dividing the random effect variance by the total variance. And we're going to be calculating this by hand. Another effect size that we're going to be measuring is the pseudo R-squared value, which will not be comparable to the OSL R-squared values on the same data. However, what these pseudo R-squared values are telling us is the amount of variance explained in Y by fixed effects only was the marginal R-squared, and the conditional R-squared that will be getting calculated is the amount of variance explained in Y by fixed and random effects. So keep that in mind moving forward when we get into these pseudo R-squared values, which we're going to be calculating. And the pseudo R-squared values will be calculated using the Mumin package, and we'll be creating a function to get those R-squared values. So the ICCs will be calculating by hand, and the pseudo R-squared values will be having a package calculate for us. So the first thing we want to do is we want to specify a random intercept only model. And the way we do that is we simply just put in our random intercept, which is going to be team ID.f. And what that's saying is, does team ID vary on their starting points, essentially? So what we're going to do is we will go ahead and go back to our Studio script, our notebook, and do hashtag models, and then do hashtag intercept only model. and let's go ahead and name that random intercept only model. Random intercept only model. So we're going to go ahead and create a new R chunk. And we're going to name this model randint for random intercept. We're going to use the Elmer function from that LME4. We're going to rest score onto 1 just to hold our fixed intercept so that it's at 1 for us. Then we're going to do 1 just to hold that random slope constant for us. Then we're going to do team underscore ID dot f. Then we can do comma data equal teams, and then we do REML equals false. So we have the most simple things. This stands for restricted estimated maximum likelihood. We're saying that no, we want just the maximum likelihood estimate, not the restricted estimated one. Then we do summary rand int. Okay, so we go ahead and run that. Oh, I spelled something wrong. There we go. Teams. I'm gonna run that. Takes a little while to run. Okay, so I'm going to go ahead and go back to the slideshow. So when it's just a random intercept, which we've indicated here, I know that we talked about this a lot in the last unit. The random intercept here is just saying, on average, the team intercepts vary by a standard deviation of 8.979. So where students start off varies by 8.979 standard deviations, which is actually a lot. So we're having quite a lot of variation between them. And additionally, in the absence of any fixed effects or random slopes, your mean of means ends up being the fixed intercept. So it's saying the average starting value for students in this, no matter what team they're on, is 73.216. And that's the mean of means that we calculated earlier. Now we're going to be running a few more models where we're going to be adding things up to this so that that's going to change. We're going to be adding a fixed slope, and we're going to be adding a random slope as well. But for now, we've just done the random intercept, which is, again, saying that people just vary in the way that they start for the scores. Now what we're going to do is we're going to go ahead and, this is actually just a continuation where I say that the random intercept is saying on average, mean of each team varies from the grand mean by 8.979 deviations. And the fixed intercepts is in the absence of any fixed effects, this intercept represents the mean of means of our outcome variable. So I simply just explained this to you. Now we're going to go ahead and calculate the ICC. So the way that you calculate the ICC is over here. So it's 80.62 divided by 80.62 plus 71.48. And I'll show you that's this variance right here, 80.62 plus the total variance here. So that's the explained variance over the total variance, which is 80.62 plus 71.48. Okay, and then we get, when we calculate that, we get an ICC of 0.53, which is essentially saying 53% of the variance in our final test scores can be attributed to differences between teams. So we're seeing that we're explaining 53% of the variance by just looking at the differences between teams. Next, we're going to get the pseudo R-squared value. And the way that we do that, from the Mumin package, we use this function called R.squared GLMM, which stands for Generalized Linear Multi-Level Model, random, and then you indicate the model in here. So I'm going to go ahead and enter that in. So let's go ahead and let's do 3 hashtags. Hashtag, hashtag, hashtag. We'll do pseudo R-squared. And then we'll go ahead and do, it's going to be R.squared GLMM, GLMM, and then we're going to do rand int. We go ahead and run that. There we go. So I'll go ahead and don't worry about that. This is okay to have here. That's just giving you a little warning about how they calculated it. But essentially, what we're getting is that because we're have a random intercept only model, there's no what is it called? marginal r squared, because we don't have any fixed effects in the model, so we don't need to worry about that. So that'll show up later. But our conditional r squared is saying 53% of variance in scores can be explained by the model's fixed and random effects. Okay, so we're saying that 53% of the model is being explained by the fixed and the random effects with this new pseudo r squared value. Now the next thing that we're going to do is we're going to go ahead and add in a fixed slope to this, and our fixed slope is going to be risk. So remember, that was that risk score that they were given, and then we're going to see how this plays out. So the way that we're going to do that, go ahead and load it on my notes. There we go. We're going to do hashtag hashtag. We're going to do random intercept comma fixed slope, and then we're going to create a new R chunk. Okay, then we're going to name this RIFS for random intercept fixed slope is what that stands for. Use their assignment operator, LMIR. We use score regressed on 1 plus risk plus, in parentheses, 1, that bar team underscore ID dot F, comma, data equal teams, comma, REML equals false. So if we go ahead and then we do a summary of RIFs, remember that stands for random intercept fixed slope, there we go. We got our model, and I'm going to go ahead and just show what that looks like on this page here. So we should have the same values here. So essentially, we have three values now. We have random intercept, we have fixed intercept, and we have a fixed slope. So our random intercept is saying, on average, team intercepts vary by 9.128 standard deviations. It's a pretty large amount of standard deviations, actually. Think about how that is. 9 standard deviations apart from each other on average is what we're saying. The fixed intercept is saying this is the average intercept while incorporating risk. So whatever the risk is at 0, this is the average score. And then we say for our fixed slope, which is the risk, on average, team scores decrease at a rate of 2.326 units for a 1 unit increase in risk. And that's something we would expect, because as risk got higher, you would expect scores to be lower because they're on that risk scale. So it's a negative trend associated with it. Now, this is another time where I have I wanted to just plot what this looks like. So I'm just going to explain to you kind of what this is doing. You can go ahead and copy and paste this from the slideshow into it. But what we're doing is from the model R package, we're doing something called add predictions. And we're adding predictions from the team model saying, okay, where do you predict that these lines are going to be going? And all you do is you do add predictions, whatever the data set is, and then the model that we're using. So our model is risk. We're saving that into something called mod2.bplot. Then we use ggplot. We use that data set, and then we use x equals risk, y equals predicted, group it by team ID.f. That's why I like to have that team ID.f, because it makes things a little bit easier for us when we're graphing it. The geom line, so we're creating a line graph. We're setting a geom ab line, which is saying we're creating a custom line on our graph. We're saying that the intercept is 77.868, which was taken from here, from our intercept. And our slope is negative 2.326, which was taken from here, which is our fixed slope. Color, the red, size equals 3, so we're going to have a red line. And then labs, we're giving a title and a x-axis title and a y-axis title. Then when you run that, you'll get a bar that looks like this. So as you can see, with our current model, what we're seeing right now is that, okay, we have a random intercept. So intercepts can vary as much as they want to. And on average, they vary by a standard deviation of 9.128. So it's saying on average these are varying by a standard deviation of 9.128. However, we didn't allow slopes to vary, so they simply all are the same slope. In our next model, we're going to allow slopes to vary, and we're going to see that things are going to change a bit. And this red line is just representing the average intercept and the average slope. And the average slope and the rest of the slopes are the exact same, which is negative 2.326 that we got from here. So you can go ahead and you can copy in this code, and it should get you the correct graph if you'd like to do it. Otherwise, just view it as from here. And notice how we're going from the x-axis is risk quintile. So as risk goes up, the score goes down by a slope of 2.326. So we can go ahead and we can calculate our ICC value again, which is 83.33 divided by the total. So it's so when I go up here, it's 83.33 divided by the total variance. So with your explained variance over the residual variance is where we're getting those numbers from. And then we do the r squared.glmm on our risk value. So I'll go ahead and do that. So go ahead and go back to our studio and do that. So we'll do hashtag pseudo r squared value, and then we'll do the r dot squared glmm, and then we'll do our risk. So random intercept fixed slope. Here we go. And I'll go ahead and go back. So what we're saying is 7% of the variance in the scores can be explained by the model's fixed effects alone. So just saying the fixed effects, so that risk quintile part that we put in the fixed side of the model is how much we're explaining. And then our R squared conditional is saying 62% of the variance in scores can be explained by the model's fixed and the random effects. So that random intercept and that fixed slope that we're associated with it. So 62% of the variance can be explained with that. Okay, so the next thing we're going to do is we are going to add in a random slope as well. The random slope with fixed intercept. So we're going to name this RSFI. And what I'm going to do is we're going to run this model, and then I'm going to show you another visualization as to what's happening as well. So let's go ahead and do our RSFI, which is random slope fixed intercept. So do hashtag random slope fixed intercept. Insert in our chunk. So we do RSFI, random slope fixed intercept, use the Elmer function from the LME4 package. We're going to regress score, tilde, 1 plus risk. So risk is going to be a fixed slope, and then 0 plus, and it's also going to be a fixed intercept, a random intercept at the same time. Team underscore ID dot F, comma, data equal teams, comma, REML equals false. So, and then we do summary, RSFI. So, assuming everything is correctly labeled in there, so we have a random slope, which is our risk, and a fixed intercept. And there we go. So we go RSFI. Okay, so then we can go ahead and look at this. So what we've done by putting that 0 is fixing our intercept. And so what we see here is we have the team ID.F, which is risk. So on average, team IDs vary by a total of 3.364. We still have a fixed slope in there. And then our fixed intercept is the average intercept while incorporating risk is 77.868. Our fixed slope is saying on average team scores decrease at a rate of 2.326 units for a 1 unit increase in risk. And that 0 that we plugged in is for random effects to indicate the intercept is fixed. So we haven't done that. we fixed our intercept, and we just have a team ID.riskf random intercept here. So again, we're going to go ahead and plot this. I gave you the code to do it. It doesn't look too much different than the other thing. The only thing that changes is the model that we're using. So we're using the RSFI. And to show you what's going on is we fixed our intercept. Now, so all values go from the average intercept, but the slopes are random from this model. So what we're saying is, on average, slopes vary by a certain amount, and the intercepts are all the same. So that's what we're doing here. The next thing that we're doing is allowing slopes and intercepts to vary totally. So, and then we're going to calculate the R-squared value. So this value is, we use 11.32 plus over the total residuals. It ends up being 0.13, so 13% of the variance in the final test scores can be attributed to difference between teams. And then we also have our pseudo R-squared, which is just the R.squared GLMM using RSFI. So if you plug that in, I'm not going to do it for now. I'm just going to have you plug that in for yourself. 7% of the variance in our scores can be explained by the model's fixed effects. Now, the R-squared conditional is saying 52% of the variance in scores can be explained by the model's fixed and the random effects. So we're going to go ahead and do one more model, and this is going to be the all-random model, is what we're going to call it. And this is essentially where we're going to allow the intercept to vary, the slope to vary, and a fixed slope and a fixed intercept. So let's go ahead and run this model. So let me go ahead and get on my notes here. We're going to go ahead and do hashtag all random model. Okay. To insert a new R chunk. So we're going to name this all rand. Use an assignment operator. Use the Elmer function to score regressed on risk plus, the risk is our fixed slope, 1 plus risk. So now we're allowing our intercept to vary team underscore ID dot f, comma, data equals teams, comma, REML equals false. Then we do summary, all rand. And then I'm going to go ahead and show you what this looks like. So I think we got it right. Here we go. So I went ahead and I got all that. So that's the same thing that's shown on here. So we've got 4 different things to look at now. We have a random intercept. We're saying on average, team intercepts vary by 8.922. So we have a random intercept. We also have a random slope, which is saying on average, team slopes vary by 2.65. This is saying, so the slopes that people have from that risk score, depending on their risk quantile, vary by an average of 2.665 deviations. We have a fixed intercept, which is the average intercept while incorporating risk, which is 77.868. And then we have a fixed slope, which is saying on average, team scores decreased at a rate of 2.326 for every 1 unit increase in risk. And per usual, we did the same thing that we did before. The only difference now is we're using the all rand data set here, and then we plug in the correct slope numbers and the intercept numbers, and then we get a model that looks like this. Now you'll notice that the intercepts vary randomly. So on average, those intercepts vary by 8.922 deviations. And then additionally, our slopes vary by 2.665 deviations. So it's saying on average, the intercept here varies by a matter of 8.665, and then the slopes vary by 2.6. Okay, and then we have still have our average slope and our average intercept as well. So that's what we're getting at with this model, is we're allowing those teams to vary and say, well, what's the average? And we can't necessarily say anything about an individual team. So we allow them to vary based on their risk quantile score. And some teams did better than other teams, some teams did worse than other teams, and so forth. And that's what we're getting at with these random models. And then we can go ahead and calculate the ICC and R squared again. So we go ahead and we calculate the total uh, explained variance within our random coefficients. So it's 79.60 plus 7.21. So just to show you where those came out, 79.60 plus 7.10 divided by the total, which is 79.603 plus 7.101 plus 40.206. And then we get an average value of 0.66, or ICC is 0.68. We're saying 68% of the variance in final test scores can be attributed to differences between teams. And then we can also just use the r dot squared GLLMN function and plug in our model, which is all rand, and we're saying 7% of the variance in scores can be explained by the model's fixed effects only, but 73% of the variance in scores can be explained by the model's fixed and random effects, essentially. So you see why having these fixed and random effects really adds a lot more than variation and explained variance, is that we're explaining 73% of the outcome of score based on our model's fixed effects and the random effects, whereas just looking at the fixed effects alone, it's only 7%. So you can see the value of the added uh, uh, random effects. So then what we can do is we can go ahead and compare our models with each other. We're going to be comparing the random intercept with the all rand, the RIFs with the all rand, and the RSFI with the all random model. And we're going to say, is the all random model the best model? So essentially, if you just go ahead and you type in ANOVA random intercept, comma, all rand, you'll be comparing the random intercept with the all random model, and you'll be getting this total here. And what we're saying is, yes, the all random model explains significantly more variance than the random intercept fixed slope model, or the random intercept models. I'm sorry, that's wrong on here. I'll change that before we do that. And then we're saying the random intercept fixed slope model, is it significantly different from the all random model? And say, yes, it is significantly different from the all random model. Then finally, we say, is the random slope fixed intercept model different than the all random model? And we say, yes, it is. So in reality, the conclusion is the random effects significantly improve model fit. So when we add in the random slopes and the random intercepts, it significantly improves our model fit. So it's worth it to include both of those. And that ends off our lesson on multi-level models. Multi-level modeling is a very complex topic. We're really just scratching the surface with this. But I think with this, you have the skills you need to go ahead and to add in and run your own multi-level model. So I have an activity for you. It's on the Module 9 lab. Module 9 lab, Psych 63 Module 9 assignment.pdf. You'll be using the popular.csv dataset to be running your own random effects models, your own multi-level models. And that's pretty much all I have for me. So thank you so much.